This is the second video in a series on the Helios radiation model. In this video, we'll talk about modeling solar radiation. We'll basically go through everything that you need in order to set up a radiation simulation over a day or over multiple days. We'll talk about linking with the SolarPosition plugin in order to specify the direction of the sun as well as specifying solar fluxes. We'll talk about how you can load weather data from file in order to drive those calculations, as well as how you can calibrate the SolarPosition model against weather station data. So as was mentioned, we'll be using a new plugin called the SolarPosition plugin. The name is a little bit of a misnomer. It was originally developed just to give you the position or direction of the sun, but it has since been expanded to give you fluxes coming from the sun, so direct as well as diffuse radiation fluxes and direct diffuse partitioning, as well as the long wave radiative fluxes emanating from the sky. Okay, let's jump right into our code example. We'll build this up piece by piece as we go through. I've already gone ahead and set up a new project. I've called it Radiation Part 2. It contains a build directory. Let's take a look at our cmakelist.txt file. I'm calling my executable Radiation Part 2. The plugins that I'm including are the Visualizer, Radiation, and SolarPosition plugins. We'll be using this CSV file, which contains weather data. I've already copied it into this project directory. We'll be using this a little bit later in this tutorial. You can find the main.cpp file for this tutorial, as well as this CSV weather data. You can find that in the lab website. You can also find a link down in the description of this video. Here is my main.cpp file. The headers that I'm including map to those three different plugins. In our cmakelist file, we have visualizer.h, radiationmodel.h, and solarposition.h. I'm using the Helios namespace, and here I have a blank main routine. Just a couple of reminders on setting up a new project. Make sure that you've loaded this new cmakelist.txt file in the project that you're working on currently. It's possible if you were following along and using the Radiation Part 1 project, you might still have the cmakelist.txt loaded. So make sure that you've right-clicked here on the cmakelist.txt and reloaded it, or follow the steps needed in VS Code if that's what you're using. And then make sure there's this little blue box next to the cmakelist file in this main.cpp file. Also make sure that you've selected in this dropdown your configuration for the executable that you're working on currently. And then I've gone ahead and rebuilt it. If you've just copied over this folder, the build directory might contain some files from the previous project you were working on. If something's going wrong in your build, it's always good practice to go ahead and clear out that build directory and then start from scratch. You can just manually delete all the files in this build directory, or you can come to the CMake tab here and then go to this gear icon and then go to reset cache and reload project, so that will clear everything out for you and start over again. We're going to start by loading in some model geometry and then setting up a basic radiation simulation. I won't go through it in as much detail as previous tutorials. We've seen this multiple times now, and I don't want to repeat myself in every single video. Basically, what we're going to do is to load in this tree.ply file that's included with Helios. We're going to add a tile ground surface and then set up the basic radiation model. All right, here's the code to get going. So I've declared an instance of the context. I'm going to use the load.ply method to load this tree.ply model. It's going to be up 3 directories to get to this ply directory and then tree.ply. I'm going to just put it at the origin, 0, 0, 0. You're going to need to scale this model because the actual dimensions are very large, and so we're going to scale it to have a height of 4. And then apply no rotation to it. I'm storing the output UUIDs for this model into a vector called UUIDs underscore tree. Then I'm going to add a tile to make up the ground. We'll put it at the origin. I'm going to make it 7 by 7 meters in size, no rotation, and then we'll give it 50 by 50 subpatches to make up that tile surface. And then while we're at it, let's just go ahead and set the two-sided flag to be 0 since this will be our ground surface. And then I've just pasted in some basic visualizer code. I'll use the Phong lighting model to give it some shading, and then we'll make a plot. So I can go ahead and run this. And there we have the visualization of our tree within our ground patch surface. By default, this model has gray primitives. You could change that if you wanted to by setting the primitive color. And this is a medium-sized model. It's about 300,000 primitives in this tree. So it doesn't load instantaneously, but it's not super slow. Now I'll go ahead and set up a base radiation simulation. You can use these fancy little macros if you like, or just type out the code. So I'll do the radiation basic. And you can tab through these if you want to change the names of things. I'm going to call this one PAR instead of shortwave. And then let's go ahead and add a shortwave band using the macro radiation shortwave band. Again, we can tab through. I'm going to call it PAR. And then we just need to delete this line because this macro added the add radiation band call. So this is going to set up a collimated radiation source. By default, you could change that to a different type of source, like a sun sphere source. It's disabled the emission for us. It's set the diffuse radiation flux to 0 and then set the source flux to 500, just picking arbitrary values to start. And then it doesn't do any scattering unless you enable it further. And then it updates our geometry and then runs the band. First, I want to illustrate the diffuse radiation. We didn't really talk about that in the previous tutorial, so I can show how that works here. Maybe we can go ahead and change this to 100 for our flux for the diffuse, and then I'll just turn off my direct radiation by setting the flux to 0. The other thing we need to do is to change our visualization so that we can visualize our radiation flux. So I'll just change this to visualizer color context primitives by data, and then we'll do radiation underscore flux underscore par, following the convention we discussed previously. And I'll go ahead and run this. This is going to give us an incorrect result, and we'll discuss why that is. All right, we set our diffuse radiation flux to be 100, and our diffuse radiation is isotropic by default. So regardless of where our primitive is oriented, it shouldn't be able to receive more than 100 watts per meter squared. But you can see that we have some primitives that are receiving up to 128 watts per meter squared. So it's about 25 more than is physically possible. And I did this to illustrate the importance of considering your boundary when it comes to diffuse radiation. As we discussed in the past lesson, diffuse radiation comes from all directions. It even comes from below in order to ensure consistency. So some of these primitives are getting diffuse radiation that are coming up from the bottom, and so we can get extra high fluxes. The way to get rid of that is to enforce a periodic boundary condition, so it effectively blocks off any radiation that might be coming up from below. So we would want to add a call here to enforce periodic boundary condition, and then we'll do XY to apply it in both the X and Y directions, and then we can run it again. And there we go. We don't have any primitives with radiation more than 100 watts per meter squared. You'll notice that our ground looks a little bit noisy here. We can kind of see some random variation when we go out onto the fringes. If that is troublesome for you, you can increase the diffuse ray count. By default, it's 1,000, but you could set it to something higher. So you do set diffuse ray count. You have to give it the label for a band, which in this case is par. And then you could do something like 5,000 or 10,000. Just keep in mind that if you set it to be 10,000, then your simulation is going to take 10 times longer to run, but you should get a smoother radiation field if that's what you're after. So we'll go ahead and keep it to the default for this example here. The next thing I want to do is to introduce the SolarPosition plugin. And a great place to start is always the documentation. So let's open up the documentation here, go to plugins, and then SolarPosition model. We can see this little table that tells us what we've already kind of done. We need to add this to our CMake list file. We've got our header file that we already included. Our main class is going to be called SolarPosition in upper camel format. We have two different possible constructors that we can use to initialize our plugin. One of them takes a pointer to the context as its only argument, and the other takes a pointer to the context as well as our offset from UTC time, our latitude, and our longitude. If we don't provide it the latitude, longitude, and offset to UTC, it will assume a default, which is basically to assume that you're in Davis, California. If we want to explicitly specify these things, then we need to use the second version of the constructor in order to explicitly set those values. And this table here tells you the convention for how to do that, which way is positive and negative as far as specifying latitude and longitude, which way is positive for UTC offset, and what the default behavior is. We can go back to our code and I'll initialize an instance of this class. So it was SolarPosition, and then I'm just going to call it sun, and then we'll assume that we're in Davis, so I'm just going to give it a pointer to the context. So ampersand and context, semicolon at the end. So now that we've done that, what are some of the things that we can do with our SolarPosition plugin? First thing is we could use it to calculate the direction of the sun. That's kind of what the plugin was originally meant for. In order to do that, we need to set the date and time within the context. There is a default date and time within the context already, but let's explicitly set it, and then we'll use that as the basis for calculating our solar direction. So from the context, we can call setDate, and this is going to take a date vector, or we can just specify as arguments to set date the day, month, and year, or the Julian day and the year. So any three of those options works. Let's just eliminate the need to call make date, and we'll just give the arguments ourselves. So let's say that we are the 10th day of July and it's 2021. Next, let's set our time. So there's similarly a set time method, context.setTime. And again, we can give it a time vector. We can give it a minute and hour. This will assume that the seconds are 0, or we can give it second, minutes, and hour. Let's just do minute and hour. Let's say that it is 1 o'clock p.m., so 0,13 for our minute and hour. Now that we have done that, we can call on our SolarPosition model to give us back the position of the sun. Taking a look back at our documentation, you could read through the equations for the models that are used in these calculations. And if we scroll down here to using the SolarPosition plugin, there's a description of how to get the direction of the sun, or different ways that you can do that. You can get a sun direction vector, so a unit vector that's pointing toward the sun. You can get a spherical coordinate denoting the elevation and azimuth of the sun. You can just get the sun elevation, you can get the sun zenith, or get the sun azimuth separately depending on which one of these that you want to call. So let's get our sun elevation and azimuth separately. Let's go ahead and make a variable sun elevation, and then we can call sun.getSunElevation. And this is going to do this based on whatever the current date and time is that's set in the context. Let's do sun azimuth, and then we can print that out to the command line. This is going to give us angles in radians, so let's convert to degrees. We can do rad2deg, and then sun elevation. And just so that we can test this out, I'm going to put a return statement here, and then I'll comment out where we load our geometry just so that we can run this little bit of code quickly. So our sun elevation is 70.8 degrees and our azimuth is 215 degrees. It makes sense that our sun elevation is going to be greater than 45, let's say, because we're sort of around midday, 1 o'clock. And our azimuth is in the south. It's going to be close to 180, but a little bit past that given that it's 1 p.m. I'm going to get rid of all of this, and because we're going to use it later, I'm going to get the sun direction vector and store it to a variable that we'll call on here in a minute. All right, next thing we're going to do is to get solar fluxes. Let's go back to our documentation. Helios uses the REST2 model in order to calculate incoming solar fluxes. It basically models the attenuation of radiation through the atmosphere as well as modeling scattering. It's for clear sky conditions. Only if you have clouds, then kind of all bets are off. There are a lot of complexities that go into modeling the effect of clouds on the incident solar radiation. This model takes 4 variables as inputs. It takes the atmospheric pressure in pascals. It takes the ambient air temperature in Kelvin, takes the relative humidity, and it takes the aerosol turbidity coefficient. And these are example values. We're going to define all of these and then use this to calculate our solar fluxes. Let's start by just defining values for each of these. Here in a minute, we're going to get those from weather data instead, but for now, let's just define them manually. So my air pressure, we're going to say is 101 pascals. We'll say our air temperature is 300 Kelvin. Let's take a relative humidity of 0.5, and we'll use our default turbidity of 0.05. Once we have these, we can now use our SolarPosition model to calculate fluxes. Let's start by calculating the solar flux in the PAR band. We have the option to get direct and diffuse fluxes in the PAR band, the NIR band, or the total solar spectrum. Let's define a variable called rPAR. That's going to be our incident solar flux in watts per meter squared. Again, important to note that this flux is perpendicular to the direction of the sun. This is not the flux on a horizontal surface. One of the main advantages of using the SolarPosition plugin is that it gives us that flux normal to the sun direction. So we'll call get solar flux par, and it takes our pressure, temperature, humidity, and turbidity in that order. And let's print this out. We can run that. And we get a flux of 440 watts per meter squared. That sounds reasonable. On a clear sky day in the middle of summer, we might expect a total radiative flux somewhere up to maybe 1,000 watts per meter squared. PAR represents about half of that, so somewhere around 440 sounds reasonable to me. We could also get our diffuse fraction. There's another method called get diffuse fraction, and it takes the same arguments, and we could use this to calculate our diffuse flux easily. Let's call it rPAR diff. That's just going to be rPAR, which was our total, meaning the sum of our direct and diffuse, and we just multiply that by f diff. We could also calculate our rPAR direct, which is rPAR times by 1 minus f diff. Let's write each of these out. I'll just copy and paste. And we can run that. All right, so our diffuse fraction is around 7%. It's pretty low, but it's reasonable for a clear sky day in the middle of summer. So that gives us a direct flux of about 410 watts per meter squared, a diffuse flux of about 31 watts per meter squared. And we should have everything that we need to go ahead and update our simulation. I'll clear all these comments out. I will uncomment loading of our geometry. So now let's set our fluxes based on what we've calculated. So we have our diffuse radiation flux, and let's update our source flux, which we called rPAR dir. And lastly, let's set our solar direction. There's 2 different ways that we could do that. We could add it as an argument here for our add collimated radiation source. Because we're going to be adding a loop and changing it dynamically, I'll just add it through a separate call. So you could put this down here, radiation.set source position. And we need to give it a source ID, which we called source ID, and then a direction. So we called that sun dir. You could also specify the position using a spherical coordinate as well. Here we have just a vec3. There's one more modification I want to make to my visualization just for some additional clarity. Let's set a title for our color bar so that we kind of know what we're plotting here. So we have set color bar title, and I'll call it par flux, and then give it some units, watts per meter squared. And we can run that. And here we have a more realistic simulation. We've got our sun direction that's specified appropriately, and we've got our fluxes for our par here. Now we're visualizing our par flux here in watts per meter squared. However, when we think about par, we may tend to want to work in units of photon flux density, which has units of micromoles per meter squared per second. What if we wanted to make our visualization in terms of that? We could do that by just adding additional primitive data if we'd like, and then scaling it appropriately so that it gives us the right values. So several different ways that you can do this. We can do it in just 2 lines of code here. First, I'm going to make a copy of our radiation flux par primitive data. We can do duplicate primitive data. And we want to give it an existing primitive data label and then a new primitive data label to copy it to. And if we don't give it a UUID argument, then it will just do this for all primitive data in the entire context, which is what we want. So our existing primitive data is radiation underscore flux underscore par. And then let's call our new one just PPFD. And at the moment, it's just a straight copy of all of those values. So technically our PPFD is still in watts per meter squared. So we can just scale that primitive data in order to get it in the right units. A reasonable scaling factor that you can use to go from watts per meter squared of par into PPFD is 4.57. So we could call scale primitive data. And this one needs a vector of UUIDs for all the primitive data that we want to scale. Let's just get all of them from the context. So we could do context.get all UUIDs. And then we'll give it the label to our primitive data we want to scale. That's going to be PPFD. And then the value we want to scale by, 4.57. And that should get us into PPFD. Let's change our visualization here. Let's visualize by PPFD primitive data instead of radiation flux par. And now we have our par flux is going to be in micromoles per meter squared per second. We can run that again. And here's our visualization in PPFD. We probably need to reduce our font size on the color bar a little bit because it's running into each other, but you can see that we're getting values up to about 2000, which is about the maximum PPFD you would expect on midday on a summer day. And just as a note, when you're working with other plugins that need things like PPFD, such as the photosynthesis model, you don't have to worry about doing this conversion yourself. It will just do that conversion for you. So it knows that the primitive data for radiation underscore flux underscore par has units of watts per meter squared, so it will do that conversion automatically. If it's working with the energy balance, for example, it wants actual energy units, and so it will just keep it in those particular units. The next thing that we're going to do is to load up that weather data from file, and we're going to use this for 2 purposes. The first is that we are going to use it to calibrate our turbidity. So we're going to take measured weather data and calibrate our turbidity from it. And then next, we're going to use it to actually drive our simulation so that we can do a dynamic daily radiation simulation. So we can load weather data from file in Helios using a couple different methods. One is that you could just load it from a text file on your own and then make calls to the add time series data point methods within the context. And this would allow you to kind of build it up on your own. Another way is to load it from XML file. You have to follow the Helios format on that. You can reference the documentation under File IO on how to do that. The method that we're going to use is probably the simplest and easiest, which is to load from a tabular CSV file. Typically, when you have weather data in a CSV file, you're going to have data points in time on the rows, and then each column is going to be a different data value at that particular time. Helios is pretty flexible on how it can take these tabular data files. There are a few requirements, specifically in terms of the columns that you have to have. So if we're talking about weather data, then we have a few columns that are needed in order to be able to know what the date and time is. So we have to have a date string as our column or a Julian day plus the year. And we can specify that date string in different ways, in different combinations of where the year, month, and day are. We can also have those values delimited by either a dash or a /. The default is to have the year in 4 digits and then the month and then the day. If you use something other than that, then you just need to specify that as an argument when we load up our file, and I'll talk about how to do that. We also need a column for our hour. That's the minimum sort of time field that's needed. You can also have columns for a minute or other things, but that's optional. We just need at least an hour. Any other columns are going to be parsed and then loaded as a time series. If we have a header in our tabular data file with a string, then it's going to use that as the name of our time series to reference it later, or we can manually specify what we want to name those columns as we reference them later within our code. All of this information on file IO is in the documentation. You go to user guide and then file IO. This first part talks about the structure of an XML file. If you want to add time series data to an XML file, this is the format you have to follow. And here's information about using the tabular weather data files and all the requirements, as well as some code examples. Let's go ahead and load this RadiationSampleData.csv file. Again, follow the link down in the description to download this file if you want to use it. And here is our data. We have 6 columns here. The first 3 designate the date and time. So our first column is our date string. Our format is the year, the month, and the day. Our second column is our hour. And we can specify the hour in 2 different formats. We can specify it with zeros at the end. So 1 hour would be 100, etc. Or it can just be the hour in terms of 1, 2, 3, 4, 5. Either of those will work, and it will just figure that out when it loads it. The third column here is our Julian day. We don't actually need that for what we're going to do, but it's there. And then the rest of the columns are data values. We have our solar radiation flux. This is going to be across the entire solar spectrum, units of watts per meter squared. Then we have our air temperature. Here it is in Celsius. We're going to need to pay attention to that later because if you remember, our solar position model needs Kelvin. And then we have our relative humidity. Here it's as a decimal. This is what our solar position model needed, so we don't need to do anything here. But if it was in percentage, then we need to downscale it by a factor of 1/100 in order to get it into a decimal value. Okay, let's load up that file. We can do it just right here before we initialize the solar position model. We're going to call context.load tabular time series data. And you can cross-reference this in the documentation, but our first argument is going to be the path to that data file to be loaded. Our second argument is a vector of strings that denotes the names of all of the columns. In our file, we have a header line that has strings for each of those columns, so we can specify an empty vector here if we want, or we could override that and give it a vector with specific names. Next, we need a delimiter. Our delimiter is a comma because it's a CSV file. It could be spaces or something. The rest of the arguments are optional. So the next one is going to be a string that gives our date format. You can see the default here is our year, month, and day, but you can rearrange those in order to match whatever the format is that you're using in your file. And then the last argument is the number of header lines that you have. The default is 0, but you can increase that. In some cases, you may have multiple header lines that you want to skip, like if there's units or something like that. So you'd want to tell it how many header lines that you have such that it starts reading the data after the number of header lines. So our CSV file is up one directory, and it's called RadiationSampleData.csv. And again, we can specify an empty vector for our column headings because we already have them in our file. If you didn't want to do that, you do something like date and then maybe hour, etc. And then you could name them whatever you want. Again, you need to follow the format specified in the documentation. You need a column named date, or you need Julian day plus year, and then you need hour. But then the rest, you can name them kind of whatever you want. Our next argument was our delimiter, which is a comma in our case, and that's the minimum number of arguments. Our file follows the default as far as the date string goes, and we can just leave it as 0 header lines. It's going to give us a warning for that because we didn't specify any header labels, and so it's just going to automatically try and parse that first line anyways. So we could be explicit by saying that it has 1 header line, but it's going to figure it out anyways. Okay, the next thing that I want to do is to talk about calibrating our turbidity against our weather station data. We just assumed some value of 0.05, which may not exactly correspond to the conditions that we have at our site. Essentially, what we want to do is to determine the turbidity that will match our predicted solar fluxes with our measured solar fluxes. So imagine that we have some weather data that looks like this. We might have some clear sky days where we get this very nice sinusoidal radiation flux. We might also have some cloudy days where you get some sort of deviation from this nice clean sinusoidal flux pattern. And so in order to do the calibration, we need in our time series to have at least one completely clear sky day, because we're going to determine the clear sky turbidity that matches that. You could, in theory, give it a cloudy sky day's worth of data and have it determine kind of an effective turbidity. It's not going to be quite accurate because there are a lot of additional things besides just the turbidity of the air that goes into determining attenuation of solar radiation by clouds. This could be a first approximation, but we're going to talk about just clear sky data. So we had our guess for our turbidity, and we could substitute that into the SolarPosition model and then run it out and get some prediction of our incoming solar flux projected onto a horizontal plane. And let's say that our turbidity is off, and so we get this offset or error between our actual weather data and our predicted solar radiation flux over the day or over multiple days. And so essentially the idea is that we're going to adjust that turbidity until we get a good match between our weather data and our prediction. Fortunately, the SolarPosition plugin has a built-in routine to be able to do this calibration automatically in a single line of code. We can add it right here after we defined our turbidity. So all we have to do is call sun.calibrate turbidity from time series. And this takes one argument, which is a string corresponding to the time series data variable that contains our solar radiation flux data. We can remind ourselves what that is if we look back at our weather data here. We called that solrad with capital S and capital R. A couple of important notes here. One is that this should be the radiative flux across the entire solar spectrum, so not just the PAR, for example. If you had a quantum sensor just measuring PAR, then this wouldn't work. So we should get values up to around 1,000 or so if we're in summer with clear sky days. We also want this to be the flux on a horizontal plane. Usually when you put a radiometer out in the environment to measure the flux, such as from a weather station, you level it, so that should almost always be the case. So let's put in that string. It was solrad, add my semicolon, and then the output of this is a float giving us our turbidity value. So let's assign it to that turbidity variable. And I think it's always worthwhile to check our value just to make sure it makes sense. You could either add a breakpoint here, or we could just print it out to the console. And I'll add a return statement and comment out our input file reading just so that it runs quickly. We can do a quick check. And if I run that, we get a turbidity of about 0.06 or so, 0.0586. So that's pretty close to our default turbidity value, a little bit higher, so we'll get a little bit different radiated fluxes than if we were using our default value, presumably a bit more accurate. Okay, now we've got everything set up and ready to go in order to run a daily simulation of light interception. So I'll uncomment these parts where we read in our geometry. We'll remove this return statement. Now what we want to do is add a loop over time so that we can run our model at discrete time intervals. I'm going to run a simulation every hour for some portion of the day. So we can add a time loop here. And the first question is, where do we want our time loop? Where do we want to start? You could, in theory, start it all the way up here before you declare your radiation model. That's going to be pretty inefficient because it's going to redeclare your radiation model class on every single time iteration. It's also going to rebuild all the geometry every time, which is going to be very computationally inefficient. So we usually want to run our loops after we've updated our geometry, but before we actually run our flux calculations. So this will allow us to only update our geometry one time because it's static over time, it's not changing. So we don't need to continually update it. That would just be a waste of time. And so we can add a time loop right here. And so I'm going to loop over hours. So I'll just make a for loop where we'll loop over a loop variable, let's call it hour. And I'm going to start at some morning time, let's say 6. We'll go to hour less than or equal to 18, let's say, so 6 p.m. And then we'll do 1 hour increments. And I'll just go ahead and wrap this whole visualization part in that loop. So now we need to set the time in the context on every loop iteration. And then we're going to recalculate our fluxes and recalculate our source direction on every time loop. So we can start by first setting the date in the context based on the very first date in our CSV file. So we could do that manually and just set it to May 10th of 2020, or we could just query that first data point if we wanted from the time series. So let's try that. So we can do context.setCurrent time series point. And this is just going to set our time based on some given point in our time series data. So we need the label to some variable inside of our time series that it's going to reference for the time. Let's just do solrad since we remember that one. And then index is going to be our index through that data. So starting on the very first line, our index, or the very first row, our index is going to be 0 and then 1, so on and so forth. So let's just start it at the very beginning time point. So now our date and time should be set to May 10th, 2020 with an hour of 100 or 1 a.m. Now inside our time loop, let's set the current time in the context. Our SolarPosition model is going to reference this a little bit later once we update our calculations here. So let's do context.setTime. And we can use any version that we want. Let's use the one that takes a minute and an hour. So our minute will be 0, and then we'll set our time based on our hour variable in our loop. So it's going to update the time in the context on every single loop. Now we need to recalculate our source direction for every hour. And so we can use our SolarPosition model. Let's go back to where we calculated our sun direction up here and then move it inside of the loop. So here we had our sun direction calculation. I'm going to just move that inside of our loop. Now it's going to calculate that based on the current time. And you notice we're now getting an error here where we tried to set our source position because now sun direction hasn't been defined. Let's also move that inside of our loop. So now it's going to update the source position in our radiation model on every loop iteration. The next thing we want to do is calculate our fluxes inside of the loop rather than up here above. So let's go ahead and move all of this inside of our loop. And we want to do all of this before we're calling the run band, because this is essentially setting up all the inputs. And then when we run it, it will actually run that particular band's calculation. Now we have these weather data variables that now are just set to a static value, but really what we want is to have those updated dynamically throughout the day based on the data in our weather data file. So we can query those based on our time series. So we can say tair is equal to context.query time series data. And we can query our time series data based on a date and time, or we can query it based on an index. Let's query it based on date and time. So what we want to query here is our air temperature. If we review back to our weather data, that was called air temp. So our label is going to be air temp. And then we need the date and time, so we can do context.getDate and context.getTime. We also want to remember that our air temperature in our weather data was in Celsius, but if you remember, our SolarPosition model needs air temperature in Kelvin, so we don't want to forget to add 273 here, otherwise we're going to get crazy values. Next, let's do our humidity, so we do RH equals context.query time series data. We do, it's RELHUM and context.getDate, context.getTime. All right, we'll just assume that our atmospheric pressure is constant. We don't have that in our weather data, so we'll just keep that as a constant. Let's go ahead and move our setting of our source fluxes here down into the loop as well. Now that we've calculated them, not sure where this is from, we can delete that. So now we've got our sun direction and our fluxes all set throughout the day. Okay, the last thing that I want to do here is to make a little movie that will display a visualization of the simulation at each hour as we move throughout the day. So we just need to come down here to where our visualizer is called. And instead of calling plot interactive, which is going to open up the window and then give us an interactive plot that we can rotate around using our arrow keys and such, we just wanted to open up the window, display it for some amount of time, and then automatically close and continue looping over times of the day. So instead of calling plot interactive, we'll call plot update. And then we can pause for some amount of time using the wait function that's built into Helios. Let's wait for 2 seconds. And then we'll close the window at the end, and then it will continue on to the next time of day. As a side note, you could also print the window to file to a JPEG image. So if you called visualizer.printWindow, you could specify the file name that you want to write to, and it would take the visualizer window and then save it to a JPEG, so you could stitch those together in a movie or something like that afterward. Let's just display our image for 2 seconds. I can go ahead and run this. And here it's showing us our window for the first time of the day. Second to pop up here. There we go. It's 6 a.m. And then it's going on to the next hour, 7 a.m. I'll edit this out and speed up so you can see the whole simulation over the day, but if you're running it in real time, it's going to take quite a bit longer. All right, that's it for this video. Thanks for watching, and I hope you'll join us for the next video in this series on the radiation model.